We are moving from measuring brain energy to mapping brain shape. Traditional sleep studies look at power spectral density, which tells us how much electrical activity exists in different frequency bands. But this misses the structural architecture of our thoughts. PHINN-EEG introduces a topological time series framework to capture the geometric shape of dreaming, opening up a new dimension in neural signal analysis. Spectral methods hit a performance ceiling because they are blind to phase relationships. Two EEG signals can have identical power spectra but completely different phase coupling structures. One might be a highly organized, coherent loop, while the other is fragmented noise. By ignoring these phase relationships, current state-of-the-art dream detection models are capped at an AUC of around 0.70. Takens delay embedding allows us to reconstruct the hidden multidimensional attractor of brain dynamics. We take a single-channel or multi-channel EEG signal and plot it against time-lagged versions of itself. According to Takens' theorem, this mathematical trick reconstructs a state-space attractor that preserves the true topology of the underlying system, turning a simple time series into a geometric point cloud. Dynamic Betti curves track how the geometric features of this attractor evolve over time. Using Vietoris-Rips filtration, we grow spheres around our data points and monitor the birth and death of topological features. We count connected components with Betti, 0, loops with Betti, 1, and voids with Betti, 2. Plotting these over time gives us a dynamic signature of the dream state, showing clear differences between dream and dreamless epochs. The PHINN-EEG pipeline extracts a 340-dimensional topological feature vector for classification. First, we apply delay embedding to multi-channel EEG. Second, we compute the persistent homology of sliding windows. Third, we extract Betti curves, persistence landscapes, and entropy. Finally, we feed these features into an XGBoost classifier or a temporal fusion CNN by LSTM network to predict dream recall. We can synthesize realistic dream state EEG using a topology-conditioned rectified flow model. Traditional generative models like GNs suffer from mode collapse. PHINN-EEG uses a rectified flow matching backbone that learns straight optimal transport paths from Gaussian noise to EEG signals. By conditioning this model on our topological feature vector, we generate highly realistic synthetic brainwaves that preserve complex phase relationships. Specific topological transitions correspond to distinct phenomenological dream categories. The researchers propose 4 candidate archetypes. Fragmented states have high Betti, 0 and near 0 Betti, 1, representing dreamless sleep. Integrated states feature low Betti, 0 and sustained Betti, 1, representing structured, lucid narratives. Recurring states show oscillating Betti, 1, and desynchronized states introduce Betti, 2 voids. Topological features are projected to significantly outperform traditional spectral benchmarks. On the DREAM database, traditional PSD models achieve an AUC of 0.70 for REM dream detection. PHINN-EEG's topological ensemble is analytically projected to reach an AUC of 0.82 to 0.90. For NREM dream detection, it targets an AUC of 0.72 to 0.78, compared to the 0.586 baseline. Several methodological challenges must be resolved before clinical or consumer deployment. First, heterogeneous electrode configurations make cross-dataset generalization difficult. Second, sparse electrode montages prevent the use of spatial filters to correct for volume conduction. Finally, pre-awakening EEG windows may capture awakening dynamics rather than pure dream states, introducing temporal misalignment. PHINN-EEG represents a paradigm shift toward phase-space geometry in neural signal analysis. By proving that the shape of brain activity contains vital information missed by spectral energy, this work opens up new avenues for cognitive science. In the future, this lightweight topological pipeline could enable real-time dream monitoring on consumer-grade wearable brain-computer interfaces.